All magnetic fields originate from moving electric charges. On a microscopic level, this can come from the spin and orbit of electrons, which create tiny magnetic fields around atoms. On a larger scale, or macroscopically, magnetic fields are produced by the flow of electric current, moving charges within a conductor. For example, when current flows through a wire, it generates a magnetic field that forms concentric circles around the wire. This connection between moving charges and magnetic fields helps explain the behavior of magnets and electric currents universally. In short, whenever charges move, they create magnetic fields.
This image shows how magnetic field lines map the direction and strength of a magnetic field around a bar magnet. The arrows on the lines point from north to south, indicating the path a free north pole would follow. The closer these lines are to each other, the stronger the magnetic field in that area, which is called flux density. Also, the lines never cross, meaning the field at any point combines into a single direction, or vector. This visualization helps us understand both the direction and intensity of the magnetic forces around the magnet. The long, straight wire creates a magnetic field that radiates outward in concentric circles, with the strength of the field decreasing as you move farther from the wire.
In the case of a flat coil, the magnetic field lines concentrate more in the center of the coil, creating a stronger field there.
Finally, in a long solenoid, which is essentially a coil stretched out in a cylindrical shape, the magnetic field inside the solenoid is uniform and quite strong, making it ideal for applications requiring a consistent magnetic field. Outside the solenoid, the field lines resemble those of a bar magnet, showing how the solenoid's magnetic field extends beyond its interior. Here, we are defining magnetic flux density, represented by B, as the force per unit current per unit length of wire in a magnetic field. When a wire 1 meter long carries a current of 1 ampere perpendicular to the magnetic field, and it experiences a force of 1 Newton due to the field, the magnetic flux density at that point is 1 Tesla. This image illustrates Fleming's left-hand rule, which helps us determine the direction of force in a magnetic field when a current is present. Using your left hand, point your forefinger in the direction of the magnetic field, your second finger in the direction of conventional current, and your thumb will show the direction of the force acting on the conductor. For this to work effectively and produce maximum force, the current and the magnetic field must be perpendicular to each other. The force experienced by a current-carrying wire in a magnetic field depends on several factors, which are captured in this formula. The force is proportional to the magnetic field strength, the current through the wire, and the length of the wire within the field. Importantly, it also depends on the sign of the angle between the wire and the magnetic field direction. This means that only the part of the magnetic field that is perpendicular to the wire actually generates force. If the wire is exactly parallel to the magnetic field, the angle is 0, and since the sign of 0 is 0, no force is produced at all. In this experiment, it is possible to measure the size of the force on a wire. Here, the forces acting on the wire are explained using Fleming's left-hand rule, which tells us that the current-carrying wire is pushed upwards in the magnetic field. According to Newton's third law, there must be an equal and opposite reaction, which means the magnets are pushed downwards with the same force. The digital balance beneath measures the downward force exerted on the magnets. As the balance is calibrated in grams, we need to use F equals mg to convert the mass to a force in newtons. Bty, varying the current through the wire and measuring the force, we see that the force acting on the wire is directly proportional to the current flowing through it. This is shown by the straight line on the graph. As y equals mx plus c and f equals bli, we can deduce that the slope, or gradient of that line, equals the product of the magnetic flux density and the length of the wire within the magnetic field. By rearranging the base equation and dividing the gradient by the wire length, we isolate the magnetic flux density. Moving charges generate a field, which can be represented by concentric circles indicating the field lines. Next, the interaction between current and is analyzed. Finally, this results in a measurable force that we can quantify in the lab. This cycle takes something invisible and microscopic and makes it measurable and understandable on a larger scale.